Hello, everyone, and welcome to section 3.1 in Precalculus, exponential functions and their graphs. So far this year, we've studied algebraic functions, which include polynomial functions and rational functions. Today, we will begin the study of two types of non-algebraic functions, exponential and logarithmic. These functions are examples of something called transcendental functions. So they're different than algebraic functions. They have a unique shape. The basic shape looks like this. An exponential function is f of x is equal to a to the x. The domain is going to be all real numbers, because if you have a base to a power, you can make that power anything that you want. But its range is only going to go from 0 to infinity. I just realized I want to write this on the next page so that you can see the whole thing at once. All real numbers and 0 to infinity. The y-intercept for the base equation, for the parent equation, is always going to be 0, 1. Think about why that's true. You have the function y is equal to a to the x, where a can be anything. Let's say it's 2 to the x, or 3 to the x, or even 100 to the x. If you plug a 0 in there, anything to the 0 power is 1. So all these graphs are going to cross right at 1, unless they've been shifted left, right, up, down. The x-intercept is not going to exist. This graph is going to come along the x-axis, go through that, and then go up like that. This is a general graph. This isn't a specific one. It does not have a vertical asymptote. Sometimes people draw it sometimes they are really steep. And it looks like it has a vertical asymptote. It does not. None. But there is a horizontal asymptote. So right along the x-axis, it's going to follow that line, but not actually touch it. Now you can just memorize that, or you can understand why, which is if you were making a table, let's say for y is equal to 2 to the x, and it's easy to see why it goes up. When x is 0, 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 to the third is 8. 2 to the fourth is 16. You can see how it's just rising up. But think about what happens when you have a negative number. 2 to the negative 1, hopefully you remember that actually means 1 over 2. A negative exponent is the same as a positive exponent in the denominator. So, sorry, I can erase this little stray mark there. 2 to the positive 1. So this is 1/2. And then negative 2 would be 2 to the negative 2, which is 1 over 2 squared, which is 1/4. See a pattern yet? 2 to the negative 3 is 1 over 2 to the 3. We've already done 2 to the 3. This is 1/8. Look what keeps happening to this number. It keeps getting smaller, but is it ever going to equal 0? It's not. It's just going to keep getting smaller and smaller and smaller and smaller and smaller, but it will never actually reach 0. So we call that a horizontal asymptote. Y is equal to 0. Now, of course, we are going to shift these graphs left, right, up, down. Fortunately, they follow the same rules as every other function we've learned. If you see an x minus c, it's going to shift it right. And for x plus c, it's going to shift it left. This has not changed. If the c is at the end and it's greater than 0, it's going to shift it up and down if c is less than 0. A negative with the x will shift it across the y-axis, and a negative out in front will reflect it over the x-axis. So that should be something that's familiar to you. If you have x squared, it looks like this. If you have negative x squared, you know it flips upside down. So a negative out front is going to flip it upside down. In this next section, it's just a whole bunch of graphs. You are more than welcome to try and graph them on your own and then look at the answers. But I will give you some tips and tricks along the way if you'd like to just follow along. So interestingly, we already did y is equal to 2 to the x briefly on the other page. So let's just plot a few basic points. Anything to the 0 power is 1, 2 to the 1 is 2, and 2 squared is 4. 0, 1, 1, 2, 2, 4. 1, 2, 3, 4. The key to graphing these is knowing where the asymptote is. Notice it says draw a dashed line for the asymptote. I want to see it. So here's my asymptote, and then I can make my graph. So you only need a few points to really get a nice shape here. And voila, you have a graph. This one's going to be the same points. So I'm literally not going to make, I really cannot stress enough that I do not recommend that you make a new table where you do 0 and then do 2 to the 0 minus 3, 2 to the negative 3, 1 over 2 to the 3, 1/8. That it's just not practical. Instead, keep your same table and just move it 3 to the right. So 1, 2, 3. I'm going to pretend that this spot is my new origin. You can put little crosshairs if you want to and say, I'm going to pretend that's my new origin. If that was my new origin, my points would still be 0, 1. So at 0, 1, 1, 2, 1 from my new origin, 1, 2, and then 2, 4. 2, 1, 2, 3, 4. Now this is a horizontal shift. If you shift an asymptote, a horizontal asymptote horizontally, you're not even going to be able to see it. So the horizontal asymptote doesn't change. And now I can go ahead and make my graph using the same table of values, just shifting over 3. Much easier than trying to make a whole new table of values. Let's do the exact same thing with 3 to the x. So anything to the 0 power is 1. 3 to the 1 is 3. 3 squared is 9. I've almost reached the limit of my ability to draw them, so there's no point in doing more of them. And I don't need to do any negative ones because I have the asymptote. So the asymptote has, this graph hasn't moved left, right, up, or down, so it's still at y is equal to 0. And I'm going to go ahead and plot my points. 0, 1, 1, 3, 2, 9. Very steep. The bigger the base, I kind of missed that. The bigger the base, the steeper the graph is going to be because it's going to rise quickly. Okay. Now this negative x is going to flip the graph over the y-axis. So normally the graph would look like this, but ours is going to look like this. Okay. So let's go ahead and do that. The asymptote is not going to change. I'm going to go ahead and draw my dashed line right there. And if you want, you can make these dashed. 0, 0, 1, 3, 2, 9. If you would like to make a little dashed one so you can picture it first, you can. But notice I did it dashed because it's not my final answer. My final answer is going to flip over the axis. So this point will stay the same. This one is right there. And then this one is negative 2, 9. There we go. If you would like to go back and erase the blue one, you can, but it's not really necessary. I know that that's not your answer if you made it dashed. You can't have two solid ones because then I won't know which one is the answer. All right, let's do another one. Y is equal to 4 to the x. So I keep putting this on there because I really want you to make the parent the base. Even if I didn't ask for this, I still would want you to do it. Your life is going to be, when you get a problem like this, do this first. That's my recommendation. That's why I keep putting them on there. All right, so y is equal to 4 to the x. It's always the same. Anything to the 0 power is 1. 4 to the 1 is 4. Oh my goodness, 4 squared is 16. I'm only going to be able to graph 2 points. This is too high. So I graph 0, 1, and 1, 4. But even with 2 points, I can make a great graph because of the asymptote. The asymptote is what allows you to make a super accurate graph. I know, I'm silly, but I want it to be green because I'm going to put 2 graphs on here. That's this graph. So I would make this table of values no matter what. But now this graph is going to be 2 to the right and up 1. It is hard to have 2 graphs on the same coordinate plane, especially with the asymptotes, so I am going to erase it. But I still want these points over here. So now I'm going to go 2 to the right and up 1. This is my new origin. And if that's the origin, that's where the asymptote goes. The asymptote is always on y is equal to 0, which in this case is right there. And now I'm going to do these points on pretending that this is the new origin. 0, 1 would be right there. And then 1, 1, 2, 3, 4. So I can't stress enough that you're always just making the parent graph. That's the key. Is it possible to actually graph y is equal to 4 to the x minus 2 plus 1? Sure. When x is 0, 4 to the negative 2 plus 1, which is 1 over 4 squared plus 1, which is 1/16 plus 1, 1 and 1/16. So at 0, you should be graphing 1 and 1/16. Good luck with that. And good luck making a whole bunch of these points. It's so easy to just make the parent graph and then shift left, right, up, or down. So number 6 is a little bit tricky. I'm going to show you 2 different ways to do it, and hopefully one of the ways you will enjoy. So one way is to still make your parent graph. This hasn't been shifted left, right, up, or down, which means it's definitely going to have an asymptote right there because it hasn't gone up or down. And you can still plot a few points. So when x is 0, anything to the 0 power is 1. But here's where it's tricky. If x is 1, you're at 1/2. You can do this, but it's not a great point. What you really need is -1 because the graph is going to go like this. So the good points are going to be over here. If you keep doing points on this side, you're just going to keep getting these awful fractions that aren't going to help give you a nice graph. So if you have a fraction, you need to do negative numbers to get good points. So 1/2 to the -1 is 1 to the -1 over 2 to the -1, which flips them. Remember, a negative exponent on the bottom is a positive exponent on the top. And a negative exponent on the top is a positive exponent on the bottom. So this is 2. At -1, I'm at 2. But whew, woo-wee, that was a lot of work, right? So instead, what I recommend is if you have a fraction, 1 over 2 to the x, I would change it to 1 to the x over 2 to the x. Now, 1 to the x doesn't really matter because 1 to the anything is still just 1. And the 2 to the x, I would bring to the top and make it negative. Okay, that x doesn't matter. And then I can bring this to the top and make it negative, just like we did with this 2 to the 1. And now you can just think of it as the parent graph with 2. So 0, anything to the 0 power. So this is just parent graph. Always do the parent. Don't worry about the negative. Anything to the 0 power is 1. 2 to the 1 is 2. 2 squared is 4. So this graph would have points at 0, 1, 1, 2, and 2, 4. But since it's been flipped over the y, you can just put the points here and then here. I personally think that this is a much better method than trying to do it that way. I find the points on the parent graph, and then I just flip them. So I've given you some of the strategies that I use for solving these, making these graphs. But obviously you have a lot of freedom to do it how you want. Just make sure that they're right. So on this next section, you should pull out your calculator and make sure that you can type these in correctly. And I will show you how to do it on my calculator. Our first one is 2 to the x when x is equal to negative 3.1. So I'm going to type in 2. The button is this caret right there. And make sure that you use this negative key down here. This one means subtract. So negative 3.1. And then you just hit enter. There you go. The next one is 2 to the negative x given pi. So I want 2 to the negative. Again, make sure you use this button. If you get an error, it probably means that you used the subtract button by accident. And we do have a pi button. It's actually right above our caret key. So make sure that you don't just use 3.14. That would be an estimate, which I don't want. Make sure you use the pi button. And the last one is 0.6 to the, and this time we're plugging in 3/2. So to make a fraction, you can use a special fraction button, but when it's a simple fraction, you can use divided by means the same as fraction. So 3 divided by 3/2. And there are your 3 answers. The one-to-one property states that if you have a to the x is equal to a to the y, then x must be equal to y. Think about that. If you have 3 to the 6 is equal to 3 to the something, it's not something, you know it must be 6. Meaning if the bases are the same, then the exponents must be the same. So in our problem here, our bases are not the same, but you can make them the same by changing the 9 to 3 squared. Now that the bases are the same, you know that 2 must be equal to x plus 1. So x is equal to 1. Go ahead and try this one on your own. I'm going to change this to 4 squared. That didn't make the bases the same. So just because 16 is equal to 4 squared doesn't make it valuable to you. You always need it to be the same base. So 2 to the what would make 16? 2 to the 4. Now that the bases are the same, now you can set the two exponents equal to each other. And x is equal to 2. The number e is called the natural base. It's actually used a ton in math and science as you get older, so it's something that you're going to want to become familiar with. It does have an approximate value, similar to pi having an approximate value of 3.14. You can think of e as approximately 2.7 in your head, just so you understand that it's really just a number. So when somebody asks for the graph of e to the x, it's really not going to be that much different than just 2.7 to the x. So it's going to maintain the same basic shape going through 1 as all of our other exponential functions. For this next problem, it wants you to find f of 20 given f of x is equal to 250 e to the 0.05x. So there is not only one e button on your calculator, there's actually 2. There's this one that's right above the natural log button, and that one's always for when you're going to give e an exponent. It is possible to just have the e and then use the caret key. It's right above it, but there's no reason not to use this one, and this will help you remember that e and natural log are associated, which I realize we haven't learned yet, but it'll help them be connected for you. Just like x squared is the inverse of square root, e to the x and natural log are going to be inverses. So you can type in 250, and then you do second e to the, and there it is, 0.05. Use your x button. Oh, not x button. We want it to be 20. So times 20. And there's your answer. On these next two, we're going to be using the one-to-one property again. Because they have the same base, we can make 2x minus 1 equal to 4. To solve that, I would add 1 to both sides, and x is equal to 5/2. On this next one, again, they have the same base, so I can let their exponents be equal to each other. And this is a little review from the previous chapters. I see an x squared in my equation. What do? Whenever you have an x squared in an equation, you should set it equal to 0 and factor. Now I have to warn you, there's two ways to factor this, 6 and 1, which would make 5, or 2 and 3, which would make 5. But because I need them to either both be positive or both be negative, I am going to choose the 2 and the 3. That'll give me a 2x in the middle and a negative 3x on the outside, which would give me a negative 5x. So my two answers are either x is equal to 2 or x is equal to 3. And you can see that pretty clearly. If x is equal to 2, then you have e to the 4 plus 6 is equal to e to the 10, which is the same. If x is equal to 3, you have e to the 9 plus 6, which is e to the 3 times 5, which is 15. And that also checks. So these are my two answers. So how do we use e? Honestly, just what does it even mean, right? Well, so I'm going to explain that now. First of all, you need to know this formula. You might have remember it from Algebra 2. You have a principal. You have the 1 plus whatever your rate is divided by the number of times you're going to compound interest raised to that same n times the number of years. This is how they calculate compounded interest. So a total of $12,000 is invested in an annual interest rate of 9%. So my principal is my 12,000. The 1 is always going to be a 1. I have an interest rate of 9%. So watch out. You do have to make this 0.09. You can't leave it as just 9. And it says that we're going to try and find the balance after 5 years if it's compounded quarterly. So the reason we divide by 4 is because the bank isn't actually going to give you 9% 4 times a year. They're only going to give you a fourth of 9% 4 times a year. So then I still put that same n up here, 4 times 5 years. So let's go ahead and type this one into our calculator. We're going to start with 12,000 times the quantity, 1 plus, and we're going to use this fraction bar. Remember, it's alpha F1, enter. And that gives us the fraction. This way you can make sure it looks exactly like you need it to look and be sure that you did it right. We're doing it quarterly, which is 4, and then to the 4 times 5. So that means that they take this 9% interest, but they only give you a fourth of the interest, but then they give it to you 4 times over the 5 years, so 20 times it's compounded. And you're going to get $18,726.11. What's great about doing these on your calculator is now I can just hit second enter, and it pops back up, and it's really easy to go back and change these numbers. So now I'm going to change my 4 to monthly, so that's going to be 12. Now, unfortunately, that did overwrite my times 5, so I'm going to have to go back and rewrite that. You can use the insert button if you don't want it to overwrite. But in this case, I want it to overwrite, so I'm going to change that to a 12. So again, the bank is not going to give you the full 9% 12 times. They're going to give you a 12th of the 9% 12 times. And it does definitely make you more money for them to compound it monthly. Now, I know this question isn't on here, but what if they asked you to compound it yearly? Then I would want to change this number. And this time I'll use the insert button to show you how it works. Second insert. 365 days in a year. But then you'll also have to delete your 12. So that's how you use the insert button. 365 and 365. So look at that. You got even more money if they compounded it daily. What if they compounded it hourly? Then I would have to take 365 days and multiply it by 24 hours in a day. What if they compounded it every minute of every hour of every day, or every second of every minute of every hour of every day? This is where the concept of continuously compounded interest comes from. That's what E is. E is when this number, this 365, becomes infinitely large. Somebody figured out that there's a point of diminishing returns. The number is just not going to improve anymore. So once you have that, instead of just making that a grossly large number, you can use this formula, 12,000 E to the, and then you give the interest rate and the number of years. So E replaces this because E represents having done the compounding so often, they call it continuously. And as you can see, if you did it every second of every minute of every hour of every day, at that point, see, it only got you another $1. And there's no way to make that any better. All right, so let's do another word problem. A deposit of $5,000 is made in a trust fund that pays 7.5% interest. So right away, you might want to circle that and change that to 0.075. To change a percent to a decimal, you move the decimal over 2 places. Compounded continuously. So that means right away I'm going to need this formula, PE to the RT, which some people say PERT. It is specified that the balance will be given to the college from which the donor graduated after the money has earned interest for 50 years. There's my T. How much will the college receive? So the amount that they're going to receive is the principal, and since it's being compounded continuously, E to the 0.075 times 50. A is equal to, you can go ahead and type that into your calculator, or I know some of you are just going to wait for me to put it into my calculator. And you get $212,000, which is just amazing, right? 50 years, you started with $5,000 and ended up with 212. That is the power of compounding. The population P in millions of Russia from 1996 to 2004 can be approximated by this model. So notice that it's E to a negative number. Do you remember what that graph looks like? It means that it's going down. So the population of Russia is going down. But it's also eventually going to level out. So this means that it's going down, but at some point it's going to level off. So T is equal to 6 represents 1996. So let's just say that my graph starts at 1990 because that would be 0. And then out here, it's at 1996. According to the model, is the population of Russia increasing or decreasing? Remember, it's that negative there that lets you know the graph looks like this. So it's decreasing. Find the population of Russia in 1998 and 2000. And you can do this on your calculator. 152.26 e to the 0. There's 2 zeros there, be careful. And then you would just plug in, but what number? Not 1998. Remember, this population model has T is equal to 6 is 1996, so T is equal to 8 would represent 1998. And this would be T is equal to 10. So be really careful there. All right, the population of Russia in the year 1998 is going to come out to be 147.58 million. And then the population in the year 2000, but you're going to write P of 10, is going to be, you should still do this on your calculator and make sure you can do this on your own. Watching me do it won't help you on a quiz. Will be 146.44 million. Use the model to predict the population of Russia in 2010. So now what P is that going to be? P of 20. So again, you can just keep using second enter on your calculator. Once you've typed this in once, hit second enter and you can keep changing this number, which is really fantastic. By the way, this answer comes out to be 140.84 million people, which is so interesting because the true value, this was a model that was supposed to predict it, but the true value actually was 142.4 million. So the model was very, very close. All right, this is really the key that I want to get to, is when will the population of Russia reach 100 million? And I'm going to teach you how to do that on your calculator. So to do part D, this is actually going to be a concept you might want to use for a lot of your problems. The first step would be to put into your y equal to your equation. So I've already entered it. Again, make sure you use this negative down here for that, not the minus, or you'll have an error. But the hardest part about this problem is the window. You need to be thinking about what values you're going to want to appear, because if you just hit graph now, you're not going to see anything. This window only goes from negative 10 to 10 and negative 10 to 10. You're trying to reach 100 million, but the problem's in millions, so you really just need it to reach 100. So I go to my window, and first of all, I'm not going to have negative years, and I don't know how many years it's going to take. Let's just say it takes 20 years. And for my y, again, I'm not going to have a negative population, but I know I need to see it at 100 million, which is just 100 for this purpose because the formula already accounts for the millions. But I'm going to say 120 just so I can see the 100 clearly. So now when I hit graph, I should be able to see, oh, I still don't see anything. So maybe my window, maybe it's going to take more years than that. Maybe I need to go all the way up to 50. Let's see if I can see something now. I still can't. Window. You might be thinking it's a little bit of a guessing game. Well, that's why in section 4, I'm going to teach you actually how to solve these. Let's just say it takes 100 years. Graph. Ooh. So sometimes getting the window can be the hardest part. So this is not going to happen for 100 years that this population reaches that. So the second step is to put the answer that you want. I want to know when it reaches 100 million. Do you remember what y is equal to a number is going to look like? It's going to look like a straight line. Oh, and look at that. I still can't see it. So remember that the population in millions right now at the start of this in 1996 is up near 150. So I'm actually going to say that I want to start at 150 because I think then you'll get to see the population as it starts. And clearly it takes more than 100 years for it to go down. So let's say 120 years. So there's the population of Russia falling. Here's the line y is equal to 100. And I can figure out exactly what year that happens in. So I go to second calculate, intersect. The blue one, it's blinking, and it lists it here. So there's two ways, even if your calculator isn't colored. Enter, and now it's blinking on the second one, and it tells you which one it's going to be talking about. And then it asks you to make a guess. It looks like they only intersect once, so the guess doesn't really matter. So at 107.79 years, that's when the population of Russia is going to have fallen all the way down to 100 million people. Okay, so we got 107.79. But remember, we need to convert that into years. So if t is equal to 6 represents 1996, what they're really saying is t is equal to 0 represents 1990. So we need to take that 1990, and it's 107 years later after that. So if you add 107 to 1990, then you're going to get the year 2098, rounding this to 108. So that is the year, it's pretty far away, 2098, when the population of Russia will reach 100 million. Number 4, in 1896, a nuclear reactor accident occurred in Chernobyl in what was then the Soviet Union. The explosion spread highly toxic radioactive chemicals, such as plutonium, over 100 square miles, and the government evacuated the city and the surrounding area. To see why the city is now uninhibited, literally to this day, consider this model, which represents the amount of plutonium that remains from an initial amount of 10 pounds after T years. By the way, I was 16 that year. I remember this quite distinctly. This was a huge event in the world. So it says, sketch the graph of this function from t is equal to 0 to t is equal to 100,000, where, again, this is another one where the t is equal to 0 represents a certain year. So in the year 1986, so 1986 is going to be our 0, and they want us to go all the way up until 100,000 years later. So if I put a 0 in here, anything to the 0 divided by 24,100 is still 0, and anything to the 0 power is 1, and 1 times 10 is 10. So you're starting with 10 pounds of plutonium. We know that a 1/2, you might remember that when we did y is equal to 1/2 to the x, we switched it to 2 to the negative 1 to the x, or 2 to the negative x. So this is going to be a downward graph. So this graph is going to go down like that. That's what the sketch is going to look like. How much will remain after the 100,000 years? So P is equal to 10 times 1/2, and then you can put the 100,000 right in there, 24,100. And you can type that into your calculator, and you're going to get 0.564. So there is still, even after 100,000 years, there's still going to be a 1/2 pound of plutonium left. Okay, last problem, number 5. Let Q represent a mass of carbon-14 in grams, whose half-life is 5,115 years. The quantity of carbon-14 present after T years is represented by this formula. So the first part says, determine the initial quantity. So I've pointed it out this time, but that means when T is equal to 0. I'm not always going to tell you that. That's something you need to understand in your head, that initial means in the beginning, and in the beginning, time is equal to 0. So we can plug that in. Q of 0 is 10 times 1/2 to the 0 divided by 5,715. But 0 divided by anything is still just 0. And 1/2 to the 0, anything to the 0 power is just 1. So this is just 10. So in other words, we're starting off with 10 grams of carbon-14. Determine the quantity present after 2,000 years. Now remember, its half-life is 5,715 years. So it'll take 5,715 years just for it to go down to 5 grams. So after 2,000, there should be more than 5 grams. So you should always be thinking about your answer and whether or not it makes sense. So I'm going to plug that in. Q of 2,000 is equal to 10 times 1/2. And this, again, is where it might really help you to have, use that function on your calculator that makes the little fractions for you. And then you can be sure that you punch that in just correct. All right, let's see. I've already done this math here. Don't want to have to do it again. That comes out to 7.846 grams, which is what I said. I knew it wouldn't be all the way down to 5 because it takes 5,000 years to get down to 5. And then sketch the graph. So at 0, we're up at 10. And it is, like the other one, going to be a downward curve like that. Again, why is that? Because fractions are the same as negative exponents. And negative exponents are going to be decreasing. So y is equal to e, or any number, a, to the x is always going to look like this, or e to the x. And then a to the negative x is going to look like this. Okay, so it's decreasing and going over to 10,000. You don't have to actually find that number. You just have to know the general shape when it says sketch. All right, that is it for section 3.1. Have a great day.